Let us get into the next chapter, the shear flow in open sections. Shear flow in open sections. The shear flow is another parameter, okay, which is generated or created when if any external shear loads are acting on a beam section, shear flows are created, which is nothing but shear flow can be calculated from the shear stress, or shear stress can be calculated from the shear flow. The shear flow is denoted by the small letter q. When the shear flow is denoted by the letter q, shear flow is equal to the product of the shear stress and the thickness of the section T. Okay, thickness of the section T. So the shear flow is the product of the shear stress and the thickness T. Why this shear flow is required? With these shear flow values, we can determine the shear center location. At that location, if any external shear load acts, the beam will undergo only bending and not twisting. Very, very important. Okay. So shear center is nothing but a point to which if any external shear loads are acting, the beam or the section will undergo only bending and not twisting. Very, very important. So this is the very familiar expression, tau is equal to FA y bar by IB, which we have used to calculate the shear stress values and to plot the shear stress distribution in the case of beams we have seen. Okay. Now we introduce a new parameter, shear flow Q. Q is equal to tau into T. Okay. Now for example, if you take a wing, okay, if you cut the wing at different locations along the span of the wing, you get an airfoil section. For each and every airfoil section, okay, you can look at the shear center. So for different sections, if you look at the shear center points, and if you connect all the shear center points by means of a straight line, which is nothing but it is called as an elastic axis. Is called as an elastic axis. Now, in this chapter, we are going to learn how to determine the shear flow values and how to plot all those shear flow values for the given open section. Next chapter, in future, we are going to see shear flow in closed sections also. Okay, so the shear flows are generated not only due to shear force and also due to the torsion. Due to the application of the external torque, shear flows are also generated. Okay, if you take the torsion equation, T by J is equal to C theta by L is equal to tau by R. Tau is a shear stress. It is not only shear stress, it is torsional shear stress. So when you try to calculate the shear flow, whenever any section is subjected to torsion, means I can call it as a torsional shear flow. When a beam is subjected to bending, the shear flow generated, I can call it as a flexural shear flow. These things you must understand, okay? But generally we will call it as a shear flow, but we should know the difference between this flexural shear flow and torsional shear flow technically. Now let us see the derivation for the shear flow, how to calculate the shear flow in open sections. Okay, so I have taken a small element of sides delta S in S direction and delta Z in the Z direction and thickness T perpendicular to the SZ plane. Okay, sigma Z is nothing but the dark stress which are produced due to the bending moments or the bending action of shear loads, whereas the shear stresses are due to shear force or torsion of the closed section, that is subjected to torque for the closed section, or shear force when it is applied to an open section. So the figure shows with the direct stress as well as the shear flow. Okay, if you just replace the shear flow by tau, we can call this diagram for direct stress and shear stress. Okay, now this diagram is applicable for direct stress and shear flow. Okay, now we are going to write down the equilibrium equations along z-axis as well as s-axis. Okay, so here this is a small element. For example, if you take this small element cut from the wing skin or fuselage skin, something like that, that's why this term is included here. Hoop stress is 0, but may be caused in the case of closed section beams. If you take fuselage, it's a closed one which is having internal pressure, so definitely it will be subjected to hoop stress. In this case, we are talking about the open section, and we are taking a small element where sigma S is usually to be assumed to be 0. Now let us resolve the forces along z direction. Now z direction is nothing but the positive z direction, which is shown in the figure, and positive s direction. Okay. Now sigma z is nothing but direct stress. You can see here, right hand side sigma z we are having, and left hand side you can see sigma z plus dou sigma z by dou z into delta z. Similarly, in the s direction, sigma s and sigma s plus dou sigma s by dou s into delta s. Similarly, shear flow in z direction, okay, q and q plus dou q by dou z into delta z. Okay, that with the respective planes it is acting along s and z axis. Okay, on this face it is acting. In this space we are having q. Okay, on the other face we are having q. Okay, so in this space where we are having sigma z, q plus dou q by dou z into delta z, we are having shear force. Sorry, shear flow. Okay, the shear flow is having a unit load per unit length, Newton per meter. Please remember, the shear force is having the unit Newton per meter. That is load per unit length. Okay, so here q plus dou q by dou s delta s is acting on this small face in z direction. Now we are going to resolve the forces in z direction. Forces acting in z direction is taken as a positive. This is a positive direction shown. Okay. Otherwise, the other direction means it is taken as a negative. If you take sigma z plus dou sigma z by dou z into delta z, Newton per meter square, this is the force multiplied by area delta s into t. Newton per meter square into meter square, it becomes Newton. It is in the positive z direction, positive. Then other sigma z is the negative z direction. So minus sigma z into this surface area, which is nothing but t into delta s. T into delta s. Same surface we are having on the other side also, right? Okay. And q is acting in the q plus dou q by dou s into delta s is acting in the z direction. Newton per meter. Okay. Newton per meter. So q plus dou q by dou s into delta s, Newton per meter, multiplied by meter delta z. Delta z is the length, which is nothing but Newton per meter into meter, Newton. And this q is in the negative z direction, so minus q into delta z is equal to 0. So in this, plus q into delta z minus q into delta z, plus and minus, we can cancel each other. And sigma z t into ds and minus sigma z t into ds or delta s, whatever it is, very small quantity. Okay, it gets cancelled each other. And here if you take dou q by dou s, we are having delta s and delta z. Here also we are having delta s, delta z. Right hand side we are having 0. So dou q by dou s plus t into dou sigma z by dou z is equal to 0. This is the equation. Similarly, if you solve in the s direction, means just replace s by z and z by s, write down the equation. No need to solve and show it. Okay. Now this is the expression or the relationship between the direct stress due to bending and the shear flow for this small element. What is sigma z from the previous chapter, unsymmetrical of bending? So let me recall that here in the box. Sigma z expression is given here. So dou q by dou s plus t into dou sigma z by dou z is equal to 0. Okay. So dou by dou z of sigma z. Dou by dou z of this sigma z term, you can see here. So dou my by dou z into ixx minus dou mx by dou z into ixy. So divided by this moment of initial terms as it is into x plus dou mx by dou z into iyy minus dou my by dou z into ixy divided by the denominator as it is, whole multiplied by y. And we have seen the relationship between the shear force, bending moment, everything in the previous chapter. That is, Sy is equal to dou mx by dou z and Sx is equal to dou my by dou z. What does it mean? The load, the shear force or the load acting in y direction, that is Sy, will produce a bending moment about x-axis, that is Mx. And load acting in x direction, Sx, will produce a bending moment about y-axis, that is My. So here, dou mx by dou z is replaced by Sy and dou my by dou z is replaced by Sx. You can see here. Okay, now just dou q by dou s is equal to minus t into dou sigma z by dou z. Okay, just we are introducing this dou sigma z by dou z in this equation. We are taking to the other side, so minus t. Okay, see here t is multiplied, t is also multiplied, and minus sign. Okay, both the places you will get minus sign because we are taking this to the other side of the equal sign. Okay, so here you can see that open section, thin walled open section is given. Sy is the force, Sx is the force. I'll tell you later while solving the problem what is this S, how to take this S, from where to take S in the calculation, how to substitute the values in the integration, etc. later in coming problems. Okay. Now this is the expression. Now I want to integrate it. I want to integrate because I want Q. Okay. So here you can take it here, just multiplying by ds on either side. I'm integrating from between the limit 0 to s, 0 to s, 0 to s. Okay. So if you integrate this left hand term, I'm getting q suffix s. That is equal to shear flow. Okay. Shear flow. You could see this expression. So this is the shear flow expression for the open section. I can call it as, more specifically, this is the shear flow expression for thin walled open sections. Thin walled open section. Okay, thin walled open section. Okay, where T is the thickness. So we have assumed that here in this case, thickness T is constant throughout the section. So even the thickness might vary from section to section. That I will tell you later. We'll explain the problems, how to consider all those things. If any section is symmetric about x-axis or y-axis or both the axes, we know very well from the last chapter, Ixy is 0. The product moment of inertia is 0. So if I plug in this expression, Ixy is 0, 0, 0, 0. So Qs is equal to, this is the final resulting term which is applicable for a symmetric section if Sy and Sx values are given. Always remember, okay, in this derivation also we have taken Sy is acting upward, so positive. Sx is acting right side, positive. If the given Sy value, Sy is acting downward means you have to take it as a minus value. So minus of minus 100, say for example. If Sx is acting left hand side, 100 Newton means here minus of minus 100. Okay, so Sy upward means positive, downward means negative. Sx right side means positive, left side means negative. Very, very, very important. And also, I told you this expression is well suitable for a symmetric section, either singly symmetric or doubly symmetric. Now, for example, if any section is given, for example, if section is given which is symmetric about x-axis alone, locate the shear center or draw the shear flow distribution. Means, okay, remember the section is symmetric about x-axis alone, okay, which means that unsymmetrical about y-axis. Okay, section is symmetric about x-axis. Determine the shear flow values. Plot the shear flow distribution. Means Sy value is not given in the problem. Please, Sy value is not given in the problem. So you can keep Sy as it is. I'll tell you later while solving the problem why you have to keep it as it is, Sy. And what will happen to Sx? And always you should remember, whenever, if any section is symmetric about any axis, remember that the shear center point will lie along the axis of symmetry. So if a section is symmetric about the x-axis, the shear center point will lie along the x-axis. The section is symmetric about y-axis, the shear center point will lie along the y-axis. So if a section is symmetric about the x-axis, I have to consider Sy alone, which means that Sx is 0. That is, the shear center point is lying on the x-axis. If a section is symmetric about y axis, you have to consider Sx alone. Sy is 0. Okay. Even if you keep Sy as it is, while taking moment for finding the shear center location, Sy will get cancelled. I will tell you later while solving the problems. Sy term will get cancelled. We don't require Sy at all. Okay. Suppose for any symmetric section, whether it is a singly symmetric or doubly symmetric, if both Sy and Sx values are given, means you have to take both the values for solving the shear flow, shear flow values, and for drawing the shear flow distribution diagrams, etc. You have to consider both Sy and Sx. Okay, values are given, mentioned in the figure. Okay, even if the values are not given, if the arrow marks are mentioned Sy, Sx, you have to keep as Sy and Sx as it is for solving the problems. Very, very, very important. You should keep in mind always. Otherwise, you will be calculating. Unnecessarily you will assume some Sx value or Sy value, and unnecessarily you will calculate. You will try to calculate Ixy value for a symmetrical section also. Okay, so these are the shear flow expressions. Okay, we need to remember all these expressions, keep in mind all these expressions while getting into any problems for solving it. Okay, now we'll do a problem. Determine the shear flow distribution in the thin wall Z section shown in figure due to a shear load Sy applied to the shear center. Shear center. Okay. So I forgot to mention one more point also. I told you that when the section is symmetric about x-axis, the shear center point will lie along the axis of, along the x-axis. If it is symmetric about y-axis, the shear center point will lie along y-axis. If the section is symmetric about both the axes, the shear center point will coincide with the centroid. Very, very important. Okay, now here thin wall section is given. Okay, the flange width like h by 2 and h by 2 top and bottom both are h by 2 and thickness t is constant and overall depth of z section is h. So already we have calculated this ixx, iyy and ixy in the first chapter, and we have explained how to plot the bending stress distribution or the axis due to bending distribution. Okay, so in the topic itself I have explained how to calculate the moment of inertia ixx, iyy and ixy. So here I'm not going to explain it again. Anyway, I have shown the final values and also the steps. Try to understand from that. So ixx thq by 3 and iyy is thq by 12 and ixy is thq by 8. Okay, now this is the expression, shear flow expression. In this problem, Sy alone is given, no information about Sx. So you can blindly assume Sx to be 0. Substitute Sx to be 0 here in this expression. So if I substitute, I'm getting this term. So this is the expression for the given Z section. For the given Z section. Okay. So we know Ixx value, Iyy value, Ixy value. Substitute in this expression. So this is the shear flow expression. After substituting that, Sy by h cube 0 to s 10.285x into ds minus 0 to s 6.857y into ds. Okay, now I have to find the shear flow values at 1, 2, 3, 4, or at C also, no problem. I have to find the shear flow values. Then I have to locate the, I have to plot the shear flow distribution. Okay, the question is draw the shear flow distribution. Now I have taken a small, I'm taking a small section, that is section 1, 2. In that I have taken a small element of ds length, which is located at distance s from the point 1. Why I should start my solution from point 1? Why not from point 4? Your wish. I can start either from point 1 or point 4. Okay, why not at 3? Why not at 2? Here we should remember always the shear flow is 0 at the open ends. So at 1 and 4, the shear flow values are 0. This we studied in solid mechanics in terms of shear stress. Shear stress is always 0 at the open ends. Okay, same concept here also. At open end points 1 and 4, shear flow values are 0. So we know that definite value at point 1 and 4. So hence I can prefer the point 1 or 4. I should not choose 2 or 3 because I do not know the shear flow value at 4 directly. So directly we cannot start solving the problem. Now 1 to 2, this is the small element. And here the expression we are having shear flow expression x and y. X and y. So this is the centroid for this Z section. X is nothing but, I told you already, horizontal distance from the centroid to the small element centroid. Okay, small element. The small element centroid is not, divide by ds by 2 and all. No. You should take it as it is. Okay. Now this is my centroid. So from here to here, how much is the horizontal distance? H by 2. Okay. H by 2 minus s will be this distance. H by 2 minus s will be this distance. This is the x distance. And if you just draw the quadrant, first quadrant, second quadrant, third quadrant, fourth quadrant. Third quadrant x is negative. And this small element is located at a distance of h by 2. It is in the third quadrant. Y value is negative. Substitute this x and y. X and y. Integrate with respect to 0 to s. Later you can substitute the limits if you want. Okay. 0 to s. 0 to s. Integrate h by 2s S square by 2. Okay, I've just taken this minus sign inside. Okay, here h by 2 into s. At s at 1, at point 1, s is 0. Shear flow is 0. Mathematically, we are proving it. At 2, s is equal to h by 2. Substitute here, you get 0.428 sy by h. See, sy by h, which means that Newton per meter, load per unit length, the shear flow you need. And look at the shear flow expression term, s square, which means that the nature of the shear flow diagram is parabolic. Very, very important. Now 1 to 2 is over. At 1 is 0, at 2 we have got the value. Now from 2, this section, let us take this section. Okay, 2 to C. I told you, or already I explained in shear stress in beams chapter in solid mechanics, the previous shear stress values will be added to the next shear stress values. Here also the shear flow values are carried forward to the next section. Okay, so 2 to C, we take a small element ds at a distance s from point 2. So now we are going to calculate for 2C section. Okay, so we are carrying forward this shear flow 0.428 sy by h plus the expression, this shear flow expression, just bring it to the next, that is plus for 2C section. This is the expression we are adding this, and for 2C, the small element ds, for this x is 0 and y value is h by 2 minus s. Okay, and it is below x-axis, so minus of h by 2 minus s. Substitute x and y here, okay, you will get this expression. Okay, integrate it. After integration, you are getting this. Then at 2, s is 0. Substitute here, you will get the previous shear flow, which means that our expression is correct. Because from the previous expression also, you got the same 0.428 sy by h. Then at C, s is equal to h by 2. Then substitute that at C, s is equal to h by 2 in this expression, get the value. So at C, 1.285 sy by h is the shear flow at C. Again, you see s square term we are having. So the nature of the shear flow diagram is parabolic. Now, since I told you already the Z section is an antisymmetric section and it is subjected to Sy alone, okay, Sy alone, okay, you should remember, okay, Sy alone, okay, Sx is 0, okay. Now we check here, 4 to 3, okay, 4 to 3, small element I have taken at a distance S, okay, x value, so at 4 we know very well shear flow is 0. So x is h by 2 minus s is x. Y is nothing but h by 2. So substitute in this expression. Okay, you have to bring it as a new expression starting from O. Okay, sorry, starting from 4. So 4 to 3. Substitute x is equal to this and y is equal to this. Integrate. At 4, s is equal to 0, so q4 is 0. At 3, s is equal to h by 2, q3 is equal to 0.428 sy by h. At Q2 we got 0.428 sy by h, positive. At 3 I am getting negative. Okay, so this is the beauty of this antisymmetric section when it is subjected to Sy alone. One side will be positive, one side will be negative. Even when you look into this, when the same section is subjected to bending also, mx also, you would have felt the same values like plus value and minus value. One side is compression and another side is tension, something like that. Here also plus value, minus value, but magnitude remains the same at 0.2 and 3. So now this is the plot. Okay, so same value 0.428. Here it is shown 0.42. Okay, at 2 and 3 shear flow values, magnitude wise same. I'll tell you where this plus and minus sign has gone. Okay, I told you already the nature of the shear flow diagram is parabolic. Okay. At 1 it is 0, okay, at 1 it is 0, okay, at 2 it is positive value, okay. So you have got one positive value, okay, always you remember for antisymmetric sections, at the top and bottom flange, definitely you will have a point where the shear flow is 0, definitely you will have a point where shear flow is 0, particularly when it is subjected to SY alone. So once you calculated at 1 shear flow is 0, at 2 shear flow is 0.428 SY by H, directly you should not plot like this. That is wrong. Okay, so this is positive means, and there is also, I told you 0 point, so mark somewhere 0 point, we can find that 0 point location also. So positive, then 0, then the other value will be negative. So show the plot like this. Negative should be taken inside this. So negative I have marked somewhere the value something like this. Then make the point 0 point, then you come to the positive. So the direction of the shear flow, arrow mark, the shear flow direction. If the shear flow values are negative means, okay, see here we are taking the S direction. The shear flow value is positive means the shear flow will follow the same direction of S. The shear flow value is negative means the shear flow direction will follow a direction opposite to the direction of the S. Okay. Now here, this is the opposite direction of S. So this is my shear flow direction because negative. So this is the negative. I'm taking just a little bit inside, then making a 0 point. Then I'm taking a positive value at 2. See this arrow mark is taking the same direction of S. Okay, locate a mark. Just complete the plot like this. Stop it as it is. Then if you look at the centroid point, that is at C, you have calculated some value. Okay, come over here. Just mark like this and stop it as it is. Come to the 3/4 section. At 4 it is 0. At 3 it is negative. You can see here opposite to that of S. So that means negative, 0, positive. So it is going the same direction. So just mark like this and you take it direction like this. And this is the value, shear flow value. Okay, shear flow value like this. Then you try to complete this. Okay, now see this shear flow. Okay, this shear flow is acting left hand side. Okay, left hand side, and this shear flow is acting right hand side, and this shear flow is acting left hand side, and this shear flow is acting right hand side. Okay, so this and this are balanced by this and this. Okay, sum of these two is equal to sum of these two. It will get cancel each other if you calculate the values. I'll tell you later how to do that. And if you look at this area, okay, I can split this diagram for Web 2-3 shear flow diagram. I can split this into one rectangle and one parabola. Okay, rectangle and one parabola. Okay, so the area of this rectangle plus the area of this parabola, if you find the area, that will be equal to SY, because SY is the external load applied. This is how you have to check your answer. I'll tell you later while solving problems, okay, how to do the things, because here we are having only like in terms of alphabets like T, H, S and SY. If you get the numerical values, it is very easy to check our answers. Even here also you can check. You can check here also. For example, 0.0428 SY by H. This one, this side is H. You will get this rectangle area plus this parabolic area 2/3 into this length and to this length. Okay, so how to get this? We are having 1.428. What's the value at C? 1.285 SY by H. So here you have 1.285 H from here to here. So 1.285 minus 0.428, you will get this value. So 2/3 into this into H. So sum it up, you will get SY. Now how to find this zero location? How to find this zero location? From 1 or from 4, whatever it is. Take down that shear flow expression. Okay, take down the shear flow expression, this expression equal to 0. Okay, equal to 0 to get the zero shear force location. So by equating that, you get one quadratic equation. Solve it. This is nothing but 0.33 H I am getting. But in textbook it is given as 0.336, whatever it is. By considering first two digits, S is equal to 0.33 H, the location where the shear flow is 0. Thank you.